All right, you guys, we are about to tackle galvanic and voltaic cells. It's a good one, so buckle up, Buttercup, because here it comes. So galvanic and voltaic cells convert chemical energy into electrical energy. And the electricity is caused by the electron movement from the anode to the cathode. We start at the anode, electrons are lost there. Oh yes, there's singing in this video. So, anode to cathode. Notice alphabetical order. All kinds of tips coming your way. So let's draw two beakers. And in those beakers, we're going to put our electrodes. I should be doing this much bigger. I think I'm going to be very sorry that I didn't. And then we're going to do the wire, and here's our load on fire, which can be anything. It could be a meter, it could be a light bulb, okay, it can be anything. And we're going to put them in solution, all right? So here's our solution, okay? And the solution that we're going to choose is zinc sulfate and copper 2 sulfate. Those are the two solutions. Now each beaker contains an electrode and the metals conducting electricity. So we're going to look up on a chart the reduction values. So the reduction values, they are always listed on the chart, and they're called half reactions. And the half reactions are listed on the table. So you look up the half reactions. And so when I go, and I'm gonna write these half reactions down. So, and I look up the half reactions, and I'm just gonna write them down now. So I looked them up, and they look like this. So zinc, solid. I'm thinking. So zinc, aqueous, plus 2 electrons, yields zinc, solid, and this is negative 0.76 volts, and copper 2 plus, aqueous, plus 2 electrons, yields copper solid, and that is plus 0.34 volts. Okay, so I looked them up on the chart. Now, copper wants to accept electrons. How do we know that? So these two, I looked these up, and the charts have what we call This is their cell potential. Looks like this. Their electrode potentials. And the more negative the value, the further to the left the reaction goes. And so this is very more negative, and so therefore it wants to give up electrons. Cell potential, right? Electrode potential. Okay, and so the more negative the value, so zinc wants to give up its electrons and copper wants to get electrons. We know this because zinc wants to give up its electrons. The more negative, the shift to the left. All right, now, so zinc is going to give up its electrons. So zinc, this is zinc here, zinc, solid, zinc, and this is copper. So zinc is going to give up its electrons, and so that means that the electrons are going to be moving in this direction here, right? We start at the anode, electrons are lost there. So that means anode, electrons are lost there, losing electrodes oxidized. They go through the wire and through the load on fire. They enter the cathode and through to the cation. All right, and so the cation, the cathode, then is reduced, and reduced the cation. They start at the anode, electrons are lost there, they go through the wire and through the load on fire, they enter the cathode and reduce the cation. Okay, now, so we know the cathode is reduced. All right, which means, see, in this solution, there are all these Cu plus 2s, Cu2 pluses, and in here, there are all these Zn2 pluses, all right? All right, now, the electrons are being accepted here, and when they're accepting electrons, the copper is accepting the electrons, and it's becoming copper solid. So that means that this electrode here is gaining mass. Well, why is it gaining mass? Because the electrons are coming through here, and they're gaining, the copper is being attracted to these electrons, and it is being electroplated onto this electrode, right? Meanwhile, the zinc, all these electrons are leaving, and this zinc, as the electrons are leaving, this zinc is leaving and turning into more zinc plus. So this electron, this electrode is losing mass. Because the electrons are leaving the zinc, and the zinc is turning into zinc 2 plus and is leaving the solution because the zinc is more negative and wants to give up electrons. So how do we know what the cell potential is here? How do we know what the actual potential of this cell is? You see, a battery runs based on the cell potential. And so what's going to happen is, if we don't do something about this, back up a second. What about the salt bridge? Because it goes through the wire and reduces the cathode, right? And then what happens is, if we don't do something about if we don't do something about the electrons piling up here, because they are starting to pile up here, right? And meanwhile, all these zinc 2 pluses are starting to pile up here. So we're getting this hugely positive pile up going on here, right? So what we need to do is we need to put in a bridge. And we put in something called a salt bridge. And what the salt bridge is, it allows the anions to go back through the salt bridge, and it's going to balance things out. And the anions goes through the salt bridge back to there. And so the anions travel this direction. And as it does this, so in this case, the SO4, see the Cu plus 2 is coming in here. And so the SO4, 2 minus, would be attracted to this big positive pileup of the zinc sulfate, the zinc 2 plus here. And it's going to go back through here to neutralize this big positive charge that is piling up here. Okay? So by neutralizing that, it keeps the balance between these charges, so a big negative charge doesn't pile up here and a big positive charge, because we want to keep the charges neutral. So we start at the anode, electrons are lost there. They go through the wire and through the load on fire. They enter the cathode and reduce the cation, and the anions go through the salt bridge back to where? There. We start at the anode, electrons are lost there. See how that works? Okay, so which one is positive and which one is negative? Well, the cation is positive, and the cathode is positive, and the anode is negative. How do we know that? Because the electrons are attracted to the cathode, and that's why they leave, because they're attracted to the positive cathode. All right? So the cathode is positive. Now, the next question is, what is the E cell potential? Well, the E cell potential is equal to, now, the formula that you're going to see, I think is a little confusing, but it's E naught cathode, hang on a second, minus E naught anode. So the problem is, in order to write the full reaction for this battery, the overall reaction, because these are called half reactions. These are called half reactions. So we're going to write the overall reaction. And to write the overall reaction, we're going to flip the anode reaction. Now, why do we do that? The reason we do that is because galvanic cells have to have a positive voltage. And you can see that if you added these two together, you would get a negative voltage. So one way to look at it is you can flip the one that's going to give you the positive voltage, and that's always going to be the anode. You're always going to flip the anode, because the anode is the one that oxidizes, and since, listen carefully, both of these are reductions, I'm going to end up flipping the one that is an oxidation. I'm going to repeat that. Both of these came off of a chart, and these are both reductions. See, they're gaining electrons. So these are both reductions. So whichever one is the anode, that's the one I have to flip, because one has to be a reduction and one has to be an oxidation. So the one that's most negative, I'm going to have to flip that, because otherwise I would add these two together and get a negative number. But the number for the galvanic cell has to be positive. So I'm going to flip the most negative one. So that means I'm going to have zinc solid plus yields zinc aqueous plus 2 electrons. And then I'm going to have underneath that copper 2 plus aqueous plus 2 electrons yields copper solid. Now I'm going to cancel my 2 electrons. And when I do that, I get copper 2 plus aqueous plus zinc solid yields zinc 2 plus aqueous plus copper solid. That is my overall reaction for this battery. Okay? Now, the thing is, we learned that when we flip a reaction, we have to change the sign. So if I change the sign, then this becomes 0.76 volts. This is 0.34 volts. And then I add them together and I get 1.1 volts. And that is, in fact, the answer. So E naught cell is equal to 1.10 volts. And I think that that's confusing because this equation doesn't take into account that you flipped this. And I want to be clear because if you watch the AP video, which you're going to do tonight, you're going to see that she does not flip the 0.76. She leaves it as negative, in which case, when you subtract the anode, you're subtracting a negative. So you're basically adding the positive. But when I teach it as you flip the equation, you flip the sign, and then you add them together. So I don't use this equation, but you're going to see it in the video. And she would be saying you take the cathode, 0.34, you subtract the anode, minus negative 0.76. Okay? All right, so that gives us the E naught cell is 1.10 volts. All right, so one thing that's super important to know is that if one of these had 4 electrons and the other had 2 electrons, in order to add them together, just like with Hess's law, you would need to multiply this equation by 2. But what's very important is you would not multiply the voltage. So do not multiply voltage. Okay? You do not multiply the volts. You leave the volts just as they are. And that's one of the questions that you'll see on the test is that they'll say, give me the overall equation. And what they're trying, and then they'll say, give me the E naught cell. And what they're trying to see is, do you multiply the voltage? You do not multiply the voltage. Okay? And she's going to talk about that in the video tonight also. All right, next. So what is a volt? Okay, 1 volt is equal to 1 joule per coulomb. And we're going to talk a little bit more about this as we go further into free response questions, but I just want to give you a general idea. So a joule is sort of like energy or work. And a coulomb is like charge. So basically, this is like number of electrons, right? Because remember, charge is electricity is the number of the electrons moving. So what a volt is actually like a ratio between energy and charge. But what you need to know is that 1 volt is equal to 1 joule per coulomb. Okay? And that's going to come up as we keep moving through it. Now, what you're going to see also is, as you go through, there are actually 2 kinds of cells. And you're going to see this tonight on the video, all right? 2 kinds of cells. First of all, voltaic cells. How do you identify one? Last year on this test, my kids knew galvanic cells, galvanic voltaic cells. Galvanic cells and voltaic cells. Okay. Galvanic cells are spontaneous, they're favored thermodynamically, and they have a positive cell potential. So we just looked at one. So here, positive cell potential. So when you flip it, they have a positive cell potential. That's one of the hints that you have. You're going to flip that anode so that it's oxidized, and it is in 2 beakers, and the actual beakers and the voltage potential between the 2 of them actually cause the power. In an electrolytic cell, there's an external power source. And what's happening in the beaker, and we'll talk more about this tomorrow, but what's happening in the beaker is happening because of the power source. So this is how you run a current through a solution. There's a positive and a negative terminal. So these cells actually have negative charges. We don't do a lot with these in chemistry, but what happened last year was it was an electrolytic cell on the test, and my kids had never seen one because it was in 1 beaker. And so they looked at it and they didn't know that it had to have a negative cell potential. All they had to do was flip the equations so that the cell potential was negative, and they didn't know it. So they didn't do it. They flipped it the wrong way. So let's write that down. Okay, voltaic cells, they have positive cell potentials. Okay? So when you flip, the anode equation, the answer will be positive. All right? And then it is spontaneous, and favored thermodynamically. And we're going to talk more about that tomorrow. Okay. An electrolytic cell, and 2 beakers. Electrode in each one. Okay. An electrolytic have a negative E0 cell. When you flip, the anode Answer will be negative. So that's how you're going to know which one is the anode. It's going to be the larger one, and you're going to flip it to be negative, okay? It's going to be non-spontaneous. Unfavored thermodynamically. And it will have an external power source. Like a battery. Okay, and so here's an example of what one might look like. And this would be the battery. Okay? All right. So let's take a quick look. I know this video is getting long. Let's take a quick look at a sample problem. All right, I've already drawn it out and everything, so we're just going to do this quick problem together. All right, and then I've already put your homework up. All right, so here's a battery. It's got iron on one side, and it's got chromium on the other side. In the solution, it's got iron 3+, and in this solution, it's got chromium 3+. Here are the two reductions, all right? Here are the two reduction equations. I pulled them off of the chart already, okay? Okay, letter A, we're going to determine the electron flow and label the anode and the cathode. Letter B, we're going to write the balanced equation for the overall reaction and calculate the E0 cell. Letter C, we're going to label the electrons as positive and negative, the electrodes as positive and negative, and then letter D, we're going to indicate the direction of the anion and the cation flow in the salt bridge. Oh, dog barking, hang on. All right, so first, we know that the most negative is the anode because it's the one that's going to shift most to the left, and because these are reductions, right? So we want it to be positive, and if I flip this one and make it positive, we're still going to add them together, and it's still going to be negative. So I need to flip this one, all right? So this one, I can label this right here as the anode. So that means the chromium, let's label it, is going to be the anode. Now, I also know that the anode is going to be oxidized. Now, I try and remember oxidation. I remember this way. A and O are both vowels, and cathode and reduction are consonants. So anode, oxidation. So then I think of the song. We start at the anode. Electrons are lost there. Oh, electrons are lost there. So here go my electrons. They go through the wire. This one happens to have no load on fire because this is a very basic diagram. But the other thing is electrons are lost there. Lose electrons, oxidized. So there's the oxidized. All right, the song, right? We start at the anode, electrons are lost there. Okay, so here come my electrons. This is the direction of my electrons. Okay, that means over on this side, this must be the cathode. And it is being reduced. Okay? All right. We're doing great. Label the anode, the cathode, and the electron flow. We start at the anode, electrons are lost there. They go through the wire and through the load on fire. They enter the cathode and reduce the cation. So that means that iron is the cation. Write the balanced equation for the overall reaction and calculate E naught cell. Okay. So I'm going to flip the anode, which means what I'm going to get is Cr solid yields Cr 3 plus aqueous plus 3 electrons, and that's going to give me 0.73 volts. So because I'm making it positive, I'm not going to subtract it from the cathode. Right? Remember that equation that I said I don't like using that, because when I flip something, because of Hess's law, when I flipped it, I just flipped the sign. And then I'm going to use the cathode equation as is. 3 plus 3 electrons, aqueous, 3 electrons yields Fe solid. And that is going to stay at 0.036. Now, the other thing I want to remind you is if I had to multiply one of these in order to cancel those electrons, I would not multiply my voltage. Voltage is not multiplied, just this is multiplied so that I can get the overall reaction. Cancel my electrons, and what I get is Cr solid plus Fe 3 plus aqueous yields Cr 3 plus aqueous plus Fe solid. Okay, and calculate E naught cell. E naught cell, I'm going to add these two together, and when I did that, I get 0.69 volts. Notice it is positive, okay? Next, label the electrons as positive and negative. Okay, which direction are my electrons headed? This way. Why? Because they are attracted to the positive cation and they are leaving the negative anode. That's why. The electrons are headed toward the positive cathode. All right. Indicate the direction of the anion and the cation flow in the salt bridge. All right. So the electrons are going to pile up here. So I need to neutralize this solution through the salt bridge, which means I need something negative, because it's going to get really negative over here and really positive over here. So what I need is for an anion to head this direction and a cation to head this direction. And that, as necessary, that would neutralize. Now, they're asking only for an anion, because only an anion is going to head over in this direction if needed. But if a cation does need to go over there, it will. But they're only asking for the anion, so we don't need to put that there. All right? So the anion goes to the salt bridge, through the salt bridge, back to there. Where? We start at the anode. So we start at the anode. Electrons are lost there. They go through the wire and through the load on fire. They enter the cathode, reduce the cation, and the anion goes through the salt bridge back to where? That's what the song is about, see? All right. So that's enough. Tonight, your homework is, I'm going to assign you the 9.8 video, which explains this much better than me. And it also talks a little bit about electrolytic cells. It's kind of confusing, but do your best. And then page 932, number 48, and number 43A. Okay, so page 931, 932, and then you're going to need the chart on page 901 in order to do the homework. But I'll put all that up on Canvas. All right, you guys, I'm glad you hung in there. Thank you. All right. Here's the problem again. So here's the picture, and then here's the problem.